Scientists say they found the strongest indications yet of the possibility of life in outer space on a planet more than 120 light years away. It's actually a lot farther than it sounds. It's a little over a quadrillion kilometres. That's a 1 with 15 zeros after it. But not too far for the James Webb Space Telescope, which has detected particular gases on a planet known as K2-18b. Here on Earth, those gases are produced by living organisms, algae and other microbes. The discovery suggests the planet may be teeming with microbial life. The scientists stress they haven't yet discovered actual aliens. Nikku Madhusdhan is a professor of astrophysics and exoplanetary science at the University of Cambridge in the UK. He led the research. Welcome to DW, Professor. Let's be clear about what you're saying and what you're not. Not life on this distant planet, but something that here on Earth you believe would only be produced by living organisms.
That's correct. That is correct. So what we are saying, we are seeing hints of these molecules, which on Earth are produced only from living organisms, and they could also be produced by living organisms on this planet, but we need a lot more evidence before we can make that robust claim. We want more observations to confirm what we are finding right now, and we want more theoretical and experimental studies to make sure that those can be robustly associated with life.
And to be clear, what you are examining in order to arrive at these conclusions, these are the electronic signals passing through various gases there and back here to Earth.
That is correct. So you are seeing the star as the planet is going in front of the star. So the starlight passes through the atmosphere of the planet before reaching the telescope. Now, and when that happens, the molecules in the planet's atmosphere absorb some of the starlight and imprint their unique spectral fingerprints on the starlight. So we can work out how much of that absorption is happening of the starlight in the planet's atmosphere, and from that we can work out the composition of the planet's atmosphere.
And so how do you make your findings more robust? Do you just look at more data, or do you look at data from elsewhere?
Yeah, so one of the major results from this is that even with just one observation, we could already see tentative hints of these molecules. And that's a very big development in the search for life, because this means that with only a few more observations, we should be able to repeat the signal and increase the detection significance to a level where we can say definitely this molecule is there. And that is very important as a huge technological advancement. Of course, we also need to do the theoretical and experimental studies to establish that there is absolutely no other abiotic molecule that can produce this. But even the current step where we're at is unprecedented. This is the closest we have ever come to detecting a possible biosignature in an exoplanet.
Now, we spoke to a physicist earlier who said that gases related to those you found can be made here on Earth abiotically, he said. He said it can be made in hydrothermal vents and on comets where there is zero prospect of life. What would you say to that?
Yeah, that is actually a very good point. So yes, the comets can make a small, in one comet they found that there is a small quantity of this gas, but the problem is that a comet is a very different environment from a planetary atmosphere, which is an inherently much more unstable environment. For example, molecular oxygen that we breathe is also present on the same comet, but no one would say that oxygen would not be a good biomarker under many conditions, under Earth-like conditions. So it's the same argument. Second problem is that these molecules are produced in extremely small quantities on comets, less than 0.1 parts per billion, but the gases, the amounts that we are seeing here in this planet are thousands of times higher than what we have on Earth. So it is creating the gases at the concentrations that we want to explain, we need to explain the data is the problems. And for that, currently there is no mechanism. People have tried to do it in the lab, but still small quantities, but there is no mechanism to explain that. And that is where more theoretical, we need to be open to abiotic mechanisms. So we need to do more theoretical work and more experimental work to see if we can explain those high quantities abiotically. And if we do, that is great, right? That would be a discovery of a new chemical process in and of itself. And we would be more than happy to go down that route if we find one.
What is it like? Just help us get behind the science. What is it like when you get these streams of data and suddenly you look at something and you think, well, no, that can't be right. That can't be right. What happens then? Do you get one of your colleagues to just have a look at these numbers and does this tell you what I think it says? How does that work?
Yeah, actually, it's not too far from that, except much, much more intense in the sense that when we first see the first signals, there is some excitement that we are seeing something new, but there is also a lot of shock and caution, thinking that maybe this could be a biomarker, in which case it would have huge ramifications on science and society. So we go on a very long process to make sure it's as robust as possible through numerous blind tests. So the time we took to reduce and analyze this data and publish it is about 3 times the time we usually take to analyze and publish one data set. And that is because of how much we need to be careful in saying anything about a biosignature. And even if we detect them, we try to remain super cautious and say, let's keep our minds open and explore other possibilities.
And so how long do you think it will be before we will be able to confirm the existence of some sort of life out there?
Yeah, like all major questions in the history of science, we need to be patient to get the most robust finding, because it's in no one's interest to make a premature claim of a life detection. So in about a year or so, we should be able to get more observations if we put in the time to confirm this result, if it is correct. And then alongside, we need to do more theoretical and experimental works to robustly associate the signal with life. That could be a few years, it could be 10 years. We don't have a limit on that. But science doesn't happen in black and white in sharp transitions. It happens gradually. But the major important step is that we have started that journey. And this is the closest we have come to finding any evidence of life elsewhere in the history of science. So that is what we should be celebrating as a civilization, as a species.
Thank you so much for sparing us your time and talking us through that, Professor. Professor Nikku Madhusdhan from the University of Cambridge. Thank you so much.
Thank you very much.
Professor Sara Seager is an astrophysicist and professor of physics, professor of planetary science, and a professor of aeronautics and astronautics at the Massachusetts Institute of Technology. Welcome to DW. What do you make of these findings? There was a game we used to play when I was a kid. Is it yeah or meh?
Right now, I would say it's a nah. But it's amazing that we're at the place where we can even try.
And so what is it that makes it less than groundbreaking? Because there's been a lot of headlines today about this research, but also a lot of skepticism.
Well, there have been headlines, but the authors themselves were largely very cautious, saying that there is a signal, but the signal needs to get to a more robust level before we can be sure that the signal is real. So there are really a number of other reasons as well.
Okay. The lead scientist in this research, he says that there was only a 3 in 1,000 chance that their detection was a fluke. How strong is that as an argument?
Well, we can put it back to you and say, would you go in an airplane if there was a 3 in 1,000 chance the airplane would crash?
Oh, well,
that's the way I like to look at it.
Oh. I'm going to have to get back to you on that because I'm going to have to look at the stats.
But really, I mean, we can get more data. The community can get more data. The authors and others can get more data. So that one we can work out. We can work on that. You know, the other questions we'd want to ask are, is the signal attributed to the right gas? Or perhaps there are other gases that could be causing the signal. And the most tricky one is, if the signal is real and attributed to the right gas, is it indeed caused by life, or could it be caused by an unknown mechanism we don't know about yet?
Okay, so there's lots of known unknowns in there. And just to expand on the way this technology works, because clearly this planet is gazillions of kilometers away. So we're talking about signals being back to Earth from a space telescope and then analysed. We're not talking about looking at soil samples. So we're just looking at trying to interpret the electronic signals reaching us back here.
Exactly. That's exactly right. We're just looking at signals from a planet very far away and just trying to understand the very nature of the planet. And if there is life there and what that life is like, well, we won't know whether it's, we all want to meet the little green humanoid, but we're just looking for any sign at all, whether it's from bacteria or anything. We'll be happy when we can find it.
Well, tell us more about where we are in the search for extraterrestrial life. Are we more likely to find microbes and bacteria or little green men with ray guns?
More likely bacteria, we think. We do think that there are many places there could be life in our solar system even. Mars, beneath the surface, the acidic clouds of Venus. We have Saturn's moons and some of Jupiter's moons that look like they may have liquid. So there are many, many possibilities. And exoplanets, the planets orbiting distant stars other than the sun, instead of offering us like the quality we have of like being able to go to a planet in our solar system, they offer us quantity. There are thousands of planets out there and likely trillions in our galaxy alone.
Okay, and where do you see the most promising research being undertaken?
We all have our favorites. It's like, would you ask someone to pick their favorite child? You couldn't do that. They're all wonderful. My personal favorite is Venus right now, the acidic clouds of Venus, but exoplanets as well. And, the enthusiasm surrounding this is simply that we're the first generation in human history that has a real shot at eventually identifying signs of life beyond Earth.
And is that more likely to come from examining samples from the recent expeditions to, say, the far side of the moon or even to Mars? Or is it more likely to come from, as we've seen, this analysis of electronic data?
Well, do you know the phrase, seeing is believing? I do think it not only has to come from our solar system, but specifically from a sample return. NASA has just brought back a sample of an asteroid. The Japanese and others have brought back samples from outer space. We're just waiting till our technology is good enough to bring back rocks from Mars, perhaps the clouds of Venus. So I think in the end, it's going to have to be samples we can bring to our very sophisticated Earth laboratories rather than remote sensing of objects far away.
Help us understand why this is important. Let's say microbial life, some form of microbial life was discovered on a planet far, far away. Why is that such a big deal? What does that give us?
We've always been trying to understand our place in the universe. For millennia, people assumed that our Earth was the very center of everything. Then we understood it's not our Earth, but our sun, as Earth revolves around the sun. Later, we understood our sun was just but one of many, many stars. And it's kind of sobering to realize that all our problems here on Earth are really just not much in the grand scheme of things. So finding life beyond Earth will tell us that we're not alone, that there might be intelligent life out there somewhere, and that there's a lot more to the universe than we ever thought.
Thanks so much for talking us through that so clearly. Professor Sara Seager from the Massachusetts Institute of Technology. Thank you so much.
And to put a serious damper on my hopes, presumably, Raymond Pierrehumbert joins us now. He's a professor of planetary physics at the University of Oxford. Professor, let's start with the basics. What exactly have these scientists found on K2-18b?
Well, they have found evidence of a sulfur compound, weak evidence of a sulfur compound called dimethyl sulfide and another related one, DMSD, which on Earth, as you say, is primarily produced by single-celled life. But there are several reasons it's a complete exaggeration to say this is strongest or even particularly strong evidence of life elsewhere. Among other things, this planet is very unlike Earth, atmospheric chemistry very unlike Earth. And so there could be many ways abiotically, without biology, to produce this this substance, even if the detection is real. For example, things related to it are made abiotically in hydrothermal vents on Earth. Also, it's been found in comets where there's essentially zero prospect of active life. So even if the detection is real, and that's still subject to debate in the future. To call this even strong evidence or the strongest evidence of life is way over the top.
You mentioned that this planet is very unlike Earth. How likely is it that this planet is actually habitable? What do we know about it?
Well, actually, the sort of physics that potentially makes this kind of planet called a sub-Neptune habitable tracks back to a paper I wrote in 2011, which showed that the greenhouse effect of hydrogen on a planet like this could actually support liquid water. However, I've been engaged in climate modeling of planets like this over the years since, and our modeling says quite firmly that this planet is way too hot to have a liquid water ocean. In fact, what's most likely is that it has a liquid rock ocean that is way too hot for any kind of life to survive in.
Now, the lead scientist says there's only a 3 in 1,000 chance that its detection is a fluke. How strong is that as an argument?
Well, one indication is that the same scientist had an earlier paper with a different instrument on the Webb telescope on this planet, which purported to detect carbon dioxide. And that was a much easier instrument to deal with, and carbon dioxide is a much easier molecule to deal with. But subsequent reanalysis really eliminated, or at least cast a lot of doubt on that detection of carbon dioxide. And so we have to reserve judgment until this data has been reanalyzed. And I know I've worked with the same instrument that this new paper is using, the instrument called MIRI LRS, which is one of the detectors on the Webb Space Telescope. And with the other planets we've been looking at, even after a year, we're finding that as we learn more about the instrument characteristics, our retrievals change. And so even I would even hold back on thinking that this detection is as certain as the paper claims.
Now, you have dashed most of my hopes there, but do you think we'll be able to confirm life beyond Earth in your and my lifetime?
Oh, that's a hard question, and the question will always be, whether the signatures, the chemical signatures of life that we see, could actually be produced abiotically. I think it's likely to be another 10 to 20 years before the next generation of space telescopes can actually probe the constellation of different atmospheric chemical characteristics that would be more certainly indicative of life. But of course, we may get radio signals from aliens at some point. I'm involved in a project on that, and that would be the most certain kind of detection of all.
I'm definitely looking forward to that one. Keep listening. Professor Raymond Pierrehumbert, Professor of Planetary Physics at Oxford University. Thank you very much for sharing your expertise and hopes with us.